Alright, so this problem, it mentions that there's a figure. It says the figure shows an overhead view, and then it describes the situation. I didn't get the figure with the problem, so I'm hoping that I'm not missing any important essential information that's only shown on the figure. Based on what I have here, I think I've been able to figure out pretty much what was going on with the figure. However, if what I do in this problem is off somewhat, and I'll mention the part where I think it could possibly be off, then feel free to let me know, and I'll try to change the way that I did the solution to account for the difference. But that said, when you're missing the figure, it's always a little bit, okay, is there something on that figure that I was supposed to know that I don't? Alright. So the question says, I'll read it out, it's an angular momentum problem. It says that, but we'll see what happens with the problem. The figure shows an overhead view of a 2.5 kilogram plastic rod of length 1.2 meters. It's on a table. One end of the rod is attached to the table, and the rod is free to pivot about this point without friction. So no friction, that's good. A disc of mass 39 grams slides towards the opposite end of the rod. When I read that, I'm imagining that the disc is sliding towards the non-fixed end of the rod. So that slides toward the opposite end of the rod with an initial velocity of 33 meters per second. The disc strikes the rod and sticks to it. After the collision, the rod rotates about the pivot point. Alright, so part A says, what is the angular velocity after the two after the collision? Part B says, what is the kinetic energy before and after the collision? Alright, so I'm actually going to work this out, and I'm going to answer part B first. And the reason I want to do that is simply because then if I do part B first, I will be able to go backwards and use that information to actually answer part A. And the question, as it's stated here, doesn't say, it says, the person that asked the question says that this is an angular momentum problem. It could be worked out that way. It could be worked out as an angular momentum problem. I think in this situation it's actually a little bit easier to view it as an energy problem rather than a momentum problem. Again, if there was some part of the question that said it has to be done as momentum, then let me know, and I'll rework out the problem as a momentum problem instead of an energy problem. That said, there's nothing here that says I have to use that, so why not just use energy? It seems a little bit more direct to do it that way. So, like I said, I'm going to start with part B, and I want the initial kinetic energy. Well, that's actually not hard to find, because initially we know the disk is moving, but we're not told anything about the rod, so presumably the rod is not moving to begin with. Alright, so that means the initial kinetic energy is just going to be 1/2 mR for mass of rod times velocity of the rod squared. I'm going to try to be clear about what my variables are in this case, okay? So, and again, the energy of the... I said that wrong, I'm sorry. It's the disk, okay? It's the disk that's moving. The rod is not moving to begin with. So, it's the 1/2 the mass of the disk times the velocity of the disk squared. So that's 1/2 times... Now, the disc is 39 grams. So let me just do an aside up here. 39 grams. You can convert that if you want. It ends up being 0.00123. Let me go back one. I think I did one too many. 0.039 kilograms. Is that right? 1, 2, 3. I got it wrong. Sorry. That's a little bit. Wait. Okay. I was right. That's what it is. 1, 2, 3. Because that's 3. Move the decimal 3 places. Yeah. So that's in kilograms. And we need it in kilograms, not in grams. Kilograms are the standard unit for pretty much all physics problems. So if you see something in grams, best thing to do is convert it straight to kilograms. 0.039. And velocity of the disk is 33 meters per second. And that will be squared. And let's go ahead and work out what that is. So it was 1/2 times 0.039 kilograms. I just noticed that's an addition sign. I pressed the wrong button, I guess. And then that's times 33 squared. Okay. So it ends up being 21.23 joules. Okay. And for my final answer on this part, I want to make sure it has the correct number of significant figures, which is 3, since our mass and our velocity both have 3 significant figures. So that is 21.2 joules for the initial kinetic energy. The final kinetic energy is going to equal the initial kinetic energy. And this is because there's no friction, and we're not told about any other source of energy going into this situation, and we're not told about any other way that energy can be leaving the situation, so presumably everything's ideal and perfect, and so the final energy is equal to the initial energy, which means your final kinetic energy is 21.2 joules. So like I said, part B is actually easier to answer than part A is. And in fact, part B will help us in finding the answer to part A. Okay, so part A, we want the angular velocity of the two after the collision. Now we already know the first key fact that we need is that initial kinetic energy equals final kinetic energy. The thing we need to look at what that final kinetic energy is a little bit more. And I'm going to start by drawing a bit of a diagram. Nothing too fancy. Let's say this is the rod and it's fixed about this end, okay? I'll just put an F there so we know that's, or maybe I'll just say fixed. There. That end is fixed. And then initially you have this cylinder that's going this way with 33 meters per second. That's initial. Final, and this is the part where I am not entirely sure what's happening because I don't have the diagram. So I'm making the assumption that basically the disc comes in here, it gets to the end of the rod, and it just sticks. So like it just basically glances the end of the rod, and it just happens to stick together right where it just barely touches it, and then they both start to rotate at that point. All right, so they'll both rotate together after that. Now, you know, it's also possible that the diagram could have showed the disc basically like hitting the rod on this side and then going rotating, or maybe the disc could have come in this direction and hit the rod, and they still have to rotate this way, but that could affect what happens. I mean, to be honest, the disc could have come in from this side and hit the rod head on, and it wouldn't rotate at all. I'm assuming that's not happening, because that would, you know, then the answer to that would be kind of redundant. They just don't move. So I'm making the assumption that it was just a bit of a glancing blow and that they stick together and start rotating. And the reason I make that assumption is because basically this is the, as we'll see in a bit, that's the simplest inertia that you can calculate, is this configuration. Although the only thing that makes a difference really for the different ways that it could have hit the rod and then stuck is mainly the inertias. Like, okay, if it were to hit the rod at the halfway point, that makes a big difference, but we're told it hits the end of the rod, so it hits somewhere near the end. And the other thing I'm taking into account here is that the problem doesn't mention that the disc has any kind of a radius. So presumably, well, we'll get to that when we get to that, but just keep in mind it doesn't have a radius, so in the end I don't think it matters very much the way that the disc actually hits the rod. If it was just at the end, like I drew it, or if it hit it more on the side, as long as it's at the end of the rod and we assume it has no radius, it doesn't make a difference. I'll get back, I'll explain that more later. Okay, so that's what's going on, and we want the angular velocity. So how quickly is it rotating about that center point now? So yeah, okay, we got to unwrap what the final kinetic energy looks like a little bit. And I looked this up just so I could show you. There's a lot of formulas on here. You don't have to worry about any of them except for this one right here. It says 1/2 I omega squared. That's your kinetic energy for rotational motion. So if you have nothing but a rotation, then your kinetic energy is equal to 1/2 I omega squared. So that's what we have, 1/2 I omega squared. And actually it does resemble linear kinetic energy, which is 1/2 mv squared in more than one way. So that's, I always thought that was an interesting, an interesting part of this. Alright, so we need, the toughest part to get here is this inertia, for sure. We need to know the inertia of the rod and the inertia of the disc at the end. And when we know those, then we can add them together and get the total inertia. So let's start with the rod, because that one's easier. The inertia of the rod, you can actually look up the formula that's also on this page here. And you can see there's a number of different formulas here. We have a rod about a center, but the one we want is the rod about the end, because our rod rotates about its endpoint, not about its center. And that's equal to 1/3 ml squared. So let me go back. It's going to be 1/3 of the mass of the rod. So mass of rod times the length of the rod squared. Alright? And that's all information that we have. So it's equal to 1/3. The mass of the rod is 2.5 kilograms. And then the length of the rod is 1.2 meters. And that'll be squared. And when we work that out, the inertia for the rod, if I plug that into a calculator, is 1/3 times was 2.5 times 1.2 squared, and I think that's right, and we find out it ends up being equal to 1.2. So that inertia is 1.20 kilogram times a meter squared. Those are just the units for inertia. Take that for what it is. Those are just units for inertia. There you go. Now the inertia of the cylinder, or disc if you prefer. Why am I calling it a cylinder? I actually probably shouldn't call it a cylinder. I'll explain why I was doing that. But it's the inertia of the disc, because that's the way the problem refers to it. I mean, a disc is kind of a cylinder, right? But it's a disc. And I was calling it a cylinder because initially I thought, oh, well, we're going to have to use this formula for the inertia of a cylinder. But here's the thing. Yes, a disc is the shape of a cylinder. That's true. But the problem is this formula requires the radius of the cylinder. And our problem, if you look at it, doesn't give any mention of what the radius of our disc is. So I basically have to assume, unless there's information on the figure that shows the radius of the disc, then I'm making the assumption here that basically the radius of our disc is so small compared to the length of the rod that it doesn't really make enough of a difference that we care to calculate it. And my evidence for this, I suppose, is that the disc only weighs 39 grams, whereas the rod weighs 2.5 kilograms. So quite a bit. The rod's quite a bit heavier than the disc, presumably quite a bit bigger. Alright? That may not be true. But lacking other information, I think that's my best assumption, is that I'm going to mark that I have an assumption here. Assume that the radius of the disc is much less than the length of the rod. Okay? If that's true, then even if the disc does have a radius, it won't be a big effect on our calculations. So that said, we're not going to use this formula because that requires a radius. Instead, we're going to use this formula for a point mass. If you take your cylinder and it has no radius, it's just a point at that point. Okay? Something that's circular that has 0 radius becomes a point. So we're going to approximate it as a point. That's what we're saying here. And because of that, the inertia of the disc will simply be mr squared, where r is the distance from the center of rotation to the center of the point mass. So it will be the mass of the disc times r squared, where just keep in mind that r is the distance from the fixed point out to the center of this. But that's the mass of the disc. Again, we're assuming there's no radius on this. If this radius is actually not there, it's 0, then our disc is the length of the rod away from the center, because this is L on this length. So it would be L plus the radius of the disc, but the radius of the disc is 0. So it's just L squared. It's no longer from here to here. It's because this little portion is 0, so it's just here to here. Okay, and that's L. So this is the inertia of our disk. The disk has the mass we got before, 0.039 kilograms. And the length of the rod, we used it right up here, is 1.2 meters. And we go ahead and work that out. Times 1.2 squared. Okay, 0.056. So it ends up being a lot smaller than the inertia of the rod, but it's still something. Alright. And then for our total inertia, that's going to be the sum. It's going to be the inertia of the rod plus the inertia of the disk. Alright. When you add those together, you get 1.2 plus 0.05616. And I can just 1.256 kilogram meter squared. Yeah, okay, that works out. That's just fine. Alright, now just a reminder, we're looking for the angular velocity, which is right here. That's omega. We know what the final kinetic energy is. We know the inertia, so we can solve for omega. Let's go ahead and do that. So final kinetic energy equals 1/2 I omega squared. The final kinetic energy is 21.23 joules. That's going to equal 1/2 times I, which is 1.256, times omega squared. We solve for omega. So omega squared will equal 2 times 21.23 divided by 1.256. So then omega will equal the square root of 2 times 21.23 over 1.256. Alright. So I'm going to put square root and then a fraction under that. It'll be 2 times 21.23 divided by 1.256. So the answer is 5.814. The units will be in radians per second. You can convert to a different unit of angular speed like revolutions per minute or whatever you want. But this is the basic unit that will come out of your calculation because we used the standard kilograms and joules and all of that. So when you go through all the units, as long as you're using the correct ones, you get radians per second out. So our omega is going to be 5.81 radians per second. And it does ask for angular velocity. Technically speaking, that means I should give direction as well. But again, I don't know So for instance, okay, if I was to take this absolutely literally and assume, okay, velocity means I need direction, which sometimes it doesn't because we use velocity offhanded to mean speed, but not using that, then we, the way I drew my diagram, then ultimately it's going to turn this way, which is, I suppose that's clockwise, isn't it? Yeah, it's clockwise. So, but then again, I don't know what the diagram showed. The diagram could have had the disk coming in from the other direction, in which case it would have gone counterclockwise. Those are pretty much only two choices on a flat surface like this, clockwise or counterclockwise. So if it needs a direction, go ahead, figure out which one that is. Hopefully the diagram would make it clear. And I believe that's all the question asked for. We got initial and final kinetic energy. We got the angular, well, speed, technically, of the after the two collide, which is 5.81 radians per second. And that should be it. So if you have any questions about how I solved part of this, or you want to update, you know, my assumptions about what the diagram looks like, please do, and I will be glad to respond and try to clarify based on the new information. Hope that helped.